Good morning, good afternoon.
Yeah. So is it audible to you, sir, clearly?
Yes, am I audible?
Yes, sir. Your voice is coming in a nice way. Sir, in person candidates are joined and so online participants have also joined. So we can start the session as per your convenience, sir.
Okay. Yes, let me just start from my. Mm, Let me join my computer there. Okay. Right. Welcome back, everybody, to the final day. And thank you for staying till the very end. Those of you who are still here. Uh, uh, so just to, quickly recap. What we have been looking at. I showed you some of the tools and techniques that I've been using in my research, and hopefully they have been. I was able to introduce them to you. So starting from tensors to continuum mechanics to elasticity, and to some techniques, mathematical techniques that we use in stability problems. So this has been done so far, and I think yesterday we looked at stability problems in a lot more detail for soft materials and especially for nonlinear elasticity. Today I'm going to have a shorter session so that because I think it's the final day and you might be keen to get back to whatever you are doing. So I just want to focus on two main things today. And I'll just kind of introduce some tools and techniques that I think are not restricted to the case of soft materials, but they will be they're fairly general, and I think you can use them in many other fields of research that you have. Okay. So the two things that I want to talk about is one is a finite element software that I have used I've been using for many years in my course in my research with my students and my postdocs, which is a very powerful software. And second thing is about some methods and some techniques on constitutive modeling. So if that's okay, Aman, I think we will have a one-shot session without a break for maybe about, let's see how long it takes, and then we'll have a shorter session today. Is that fine, Aman?
Yes, sir. It's fine for us, sir, also. And I've already informed the participant that we are going to have a short session today.
Okay, fine. So let me share my screen, and I think the first thing that I want to talk about is a finite element software that I have been using quite a bit, and I want to basically give maybe just share that with you so that I hope that it will be of use to some of you at least. Because I think in the beginning, the first lecture, some people wanted to get their hands on some code, and I also have in my personal discussion with people, with a lot of students across, they would want to have hands on the code that they can directly run themselves. So what I have been, what my experience has been so far by interacting with lots and lots of students, PhD students and master students and postdocs in India is that for a lot of use cases, people tend to use some commercial software like Abacus, ANSYS, or COMSOL or something similar. And the disadvantages of a lot of commercial software is that they are very expensive. So either you pay for the license, which is super expensive, or you do something illegal to get a pirated version of the software, which is just not fair, not nice. But I would just want to introduce you to this DL2 library. DL2 stands for Differential Equations Analysis Library, and it is in C++. So it's a fairly common language, and you can install it on your computer just today itself if you want to. It's very general purpose. And I will just show you a couple of features of this library so that you can go ahead and, if you want to use, go ahead and use it. Okay. So the web page is just simply del2.org, dealii.org. So you can just go ahead and on your computer. So there are a couple of steps. One is, you of course have to download and install it. And the second step is using it. So what in my experience has been that for majority of students, the first step, like that is downloading and installing, is a fair challenge. So I just want to quickly show you how to do that. So you go to the download area, and instead of installing DL2 on your computer, which takes up a lot of time, you can go down and get a virtual image. Okay, so for those of you, if you're into this scientific computing, or if you're doing any simulations, hopefully you are familiar with virtual machines and Docker. If not, it's not a big deal. It's just very simple. So you basically, essentially what it does is, it creates an entire virtual Linux environment on your computer. Does not matter whether you have a Windows or a Linux or a Mac machine. It can be anything. You just get Docker. Docker is sort of a kind of a software which creates virtual environment on a computer, and through this link you can basically get entire DL2 installed on a virtual Linux on your computer, and you can run it. Okay, so you don't have to spend a lot of time in trying to understand how do I install a complex software, which is the case with a lot of libraries like that. So once you get that, you basically go onto the home page, and there is the link to documentation. And one of the reasons I ask my students and my postdocs to use DL2 is that even if you're an absolute beginner in C++ and finite element method, you can start working on it because the documentation is excellent. So if you go to documentation, there are a lot of things, but I would probably go ahead and use the tutorial programs. So you go to the tutorial, and DL2 has, so the tutorials are basically graphed here. There are too many tutorials, but if you come down, tutorials are organized by number, step 1, 2, 3, 4, 5, 6, 7, so on. And each of these, if you start from step 1, step 2, it basically gradually builds up the complexity. So step 1 is simply, how do you create a grid? Okay, so how do you create a mesh? Step 2 is simply, how do you put degrees of freedom to the mesh? Okay. The step 3 is simply, how do you solve a Laplace equation? So let me just show you. Let's say if you go to step 1, and there's a whole lot of description of how and what things happen. How do you run the command? How do you run the program within your environment? But if you look at the code itself, the code. Let me come down directly to the code. The code is very simple. Okay. So if you are familiar with any of the programming languages, or if you've done a little bit of C++, you would understand a bit. If not, I think you can maybe, if you want to learn, you can learn. So you basically include. First of all, you include the relevant libraries from the DL2. You include the relevant libraries from the DL2 itself, and then you include some simple libraries from C++, IOStream, FStream, math, and then this is the command. This is the function that basically creates a mesh. So you create a triangulation object, and you say, okay, I want to create a hypercube. I want to create a square and refine it 4 times. And you just create a file name where you would basically output your mesh, and then you basically create it. And if you go up into the tutorial, it basically explains each and every line of the code very carefully. So it will tell you, okay, what is the purpose of the include line here? What is the purpose of every single line in the code? This is how you create the first mesh. So it explains very nicely how things are done. And eventually, basically, the output looks like this. You can create a mesh. This is just a very toy problem, just to make people understand what DL2 does, but just how do you create a mesh of a square type or an angular type, and so on. You can look at a more complex example. So if I go to step 44, step 44 is the one that I use in my research. It is finite strain hyperelasticity. So if I just show you how complex that is, it basically talks about the notation, the entire mathematics of elasticity, deformation gradient, strain tensor, and then the different types of invariants, traction condition, Piola relationship, and then what kind of energy density function you would use. So in this case, for example, they've got used a Neo-Hookean energy density function. So a whole host of, it's pretty much more like, it's like a textbook. You just go to it gradually. And I'm just not showing you all the details, I just want to show you the key ideas. It teaches a great deal about the finite element method, but also how to apply that. And this is the kind of output you can get. So this is a problem in step 44, the example problem where they take a basically a box. You have a cuboid, and you are applying a load in the center of the cuboid. So in FEM, you will basically just solve only quarter of the problem because the problem is symmetric, and then you can solve like a problem with a very large deformation directly. Now the advantage is, the reason I've showed you this is that this is a code that is right there. You just have to run, and the entire code runs for you. So if you are a new person who is starting to work with finite element method, or starting to work with large deformation problems, or any problem in differential equations, you can choose the appropriate problem, press run, the problem runs, and then just go back to the code, make small changes for whatever thing that you want to do. So let's say you want to change the energy density function, you change maybe 1 or 2 lines. If you want to change the boundary condition, you change 1 or 2 lines. If you want to have a different mesh, you change 1 or 2 lines, and everything is there with you. So I highly recommend, if you are a researcher in this area, or if your research group wants to go ahead and use some of these things, I highly recommend using DL2. Installation is not required because you can directly get a virtual image from Docker. Codes are all there, so you just need to run the codes. And the biggest advantage is that, the reason that we use it is that, first of all, it is open source software, free software. So there is no license fees. There is no need to worry about, are you pirating something, or are you paying a huge amount of money for licenses. Secondly, because the entire source code is there with you, you can change it, and you can modify it. Once you become a little bit more expert, and once you have more experience, you can modify that things and get basically what you want. This is what I had done in what I showed you yesterday. If you remember, what we were discussing yesterday was how do we find the correct eigenvalues of the stiffness matrix, so that when the eigenvalue becomes 0, you look at the eigenvector, and then you move in the direction of the bifurcation. All those things can be done quite easily in DL2 because you have access to all the data structure. In a lot of commercial software, sometimes it's very hard to get out those values of the matrix, of the stiffness matrix, and so on. So it is very, very nice to have a tool like this. And thirdly, this library is developed and maintained by basically professors and postdocs and scientists all over the world. So it's a very academic-oriented library, and as a result, people are very helpful, and people are always willing to help. So if you have questions, there is a DL2 discussion forum. It's very, very useful. I've asked a lot of questions there, and people immediately reply to my answers, to my questions. In fact, because I started using DL2 in my research, and my PhD and postdoc started using that, we sort of engaged in discussion with other people, and we became collaborators with people who developed DL2. So last few of my papers have been with the collaborators who are actually developers of DL2. So we sort of developed good relationships, and learned a lot from people just because we were using the right tools and techniques. So I would, if you have already started working on problems and if you already have something, it's fine. But if you're at the stage where you're choosing, you want to figure out, okay, what should I do for my research? I think this is a great alternative to what you might have otherwise. So if I let's close this one and go back, you can see the list of all the kind of problems that they have solved. So for example, you've got Helmholtz equation, you've got elasticity, you've got advection equation, you've got a Laplace problem with higher order mappings, you've got DG, discontinuous Galerkin, you've got wave equations, you've got mixed finite elements, you've got fluid flow. So I think pretty much everywhere when you have partial differential equation, I think this is a library that can provide something to you for free with a lot of advantages. So my recommendation as a teacher is that I would love to share this thing with you, and hopefully you will find this useful. I can also maybe show one more thing. So this is the GitHub page for one of my PhD students who recently graduated, and he basically developed everything in DL2. So he developed Masood basically developed everything in DL, and then what he did was he took DL2, and then he took the entire code base and he changed that a little bit, and then he basically published his own version of DL. So this is what is basically possible with all open source software, that you can take it, you can modify it the way you want, and then you can publish your own version of a new software. And it is, first of all, it is very rewarding as a researcher to be able to do something of that scale, but also it's super nice for your CV. If you are after graduation, if you are applying for jobs, or if you are trying to start something on your own, and you can show this experience that you have experience in developing scientific software on your own, doing something on your own, then I think that would be something substantial that you can do. So you can look at his page. It's Masood Ahmadi MADL. You can look at the basically the publications that we have from this software, and it's quite nice. So just something that I wanted to share about this toolkit that we have, which can be very useful for a lot of researchers. So that was part one of my the thing that I wanted to communicate today. Try it out if you want to. It's okay if you don't want to. I think it's all the same. Right. So let's move on to part two. Let me share my other screen for that. In the meantime, any questions do you have? I'm happy to take them.
Any question? So sir, I just have a quick query. So deal 2 that you are showing.
Yeah.
So like if we are working on someone else developed thing, so how compatible it is? Like, is it possible we can change the geometry and do the modification according to our requirement? Or
Absolutely.
Okay.
It's a very modular. So the way software is written. Let me stop that. The way software is written is that the initial geometry. How do you make the mesh? How do you discretize and use the shape functions? Which differential equation you solve on it? Everything is on its own. So you can change small things here and there, and you can just modify it. So for example, what I showed you for the elasticity problem, you have a punch problem and you compress this for a super large deformation. You can start with that geometry. You can solve another problem on it. You can solve a fluid flow problem on it, or you can solve a heat conduction problem on it. Or you want to do the same elasticity problem, but with a by adding viscoelasticity or something else, then you can do it. It's just changing a few lines of code here and there appropriately and moving ahead. So everything is very modular, that you just change specific module and other things take care of themselves.
Thank you, sir. That will be of great help, sir. I think it's a very compatible thing. We can, if we utilize it, it will be good for our research work also.
Yeah, I think it's good for. So I've been advocating DL2 for many years to a lot of people, and I've made a lot of friends via this as well, and it has been quite good. So even if you don't want to like incorporate it completely, I think it's worth a try just to see the capabilities. And other thing is DL2 is not the only one, by the way. I mean, this is just one software that I think is very nice, but there are plenty of other open source alternatives to the traditional Abacus and COMSOL and ANSYS, which people essentially use a lot. And I highly recommend that if you want to develop as a researcher, if you want to, I think you should try to get trained on the good set of tools. You can get trained on poor set of tools because anyway you are doing a PhD, you are spending 5 years on learning something. Might as well learn something that is universally accepted to be nice and which has respect and which has high capabilities. So, for example, DL2, when we have large scale simulations, it very easily loads onto a supercomputer and we can run large scale simulations using parallel computing. You can't do that with Abacus. You can't do that scaling up easily. So some of my colleagues here in geosciences, they have to run simulations on super large scale models of different planets, and they need to run on clusters and supercomputers. They can't run on simple workstations, and you can't use some commercial software for that because they don't scale up so nicely. But these modular software like DL2, which are written with they are written in a more modern scientific software engineering approach. So they have higher capabilities. And now I think if you move forward, if you look ahead 5 years or 10 years, and you see what's happening in industry, and if you see what's happening across different domains, you would see that after 10 years, nobody would be using their personal computer for doing scientific computing. Pretty much everything happens either on cloud or on GPUs. And then you need to have those capabilities built in. You need to learn technology today that will be of use 5 years or 10 years down the line. You can't learn technology today that was used 20 years ago. So that's my kind of philosophy for all the students, that try to kind of look ahead in the future and learn things that will be of use in the future rather than things that were very useful 15 years ago to somebody else. So, yeah.
So, thank you very much, sir, for such informative knowledge. So, participant, do you have any question? So, we can go ahead, I think.
Okay, so I'll switch gears a little bit, and I'll come back to soft solids, which is the key, which was the main topic here. And let me, essentially I want to talk about constitutive modeling, because I think this is one topic which I didn't touch too much about. I mentioned just a little bit that, okay, if you have energy as a function of deformation gradient, then you can get stress as dWdF. So we had a look at that part, which was let's say hyperelasticity. But I want to touch upon this topic in a little bit more detail. And the idea is that this topic has been very difficult in the field of soft solids for many decades. And things have changed significantly as well in this area. So I just want to basically go through some of the changes that have happened, and maybe again prepare you for for what will happen in the next 5 to 10 years. So maybe learn the new things rather than learning what was the state of the art 20 years ago. So here is the idea. I mean, constitutive modeling, basically what it does is you want to predict the behavior of a solid under certain deformation. Okay, so you have some very nice geometry of some part. Let's say you have some machine part that looks a bit strange, or maybe it's a biological system that you want to model, and it has undergoing a very complex loading scenario, and you want to predict. Essentially, this is a problem every time. You want to predict how will this system behave under a given set of loading conditions, under a given set of boundary conditions. So we some of the things are quite certain. So we know that no matter what it happens, it is always going to satisfy balance laws, which are the basically laws of physics. Okay? So we know that balance laws are fine. The stress is going to be balanced, the momentum is going to be balanced, the energy is going to be balanced, the second law of thermodynamics says entropy is going to increase, so that will happen. If there is some friction, then the energy would be lost. So I think those kind of basic understanding is we are pretty much familiar with. But what has been a big challenge over the last many years is how is the material behavior or material model, which basically means that what is the relationship between, let's say, the stress, the strain rate, temperature, and maybe something else. We also looked at electric field. We also looked at magnetic field. So how are these quantities interlinked with each other? And this is basically what constitutive modeling does. It tells you how are these quantities inside a material are linked to each other. Stress and strain rate and temperature and electric and magnetic field and maybe chemical concentration. There's so many things that can happen in a multi-physics problem. You can have, for example, in biological tissues, if you're looking at an artery or brain, there's a lot of porous solid filled in with a lot of fluid, with some chemicals inside of it. There is some pre-stress inside of it. So there is friction going on. There is a complex process. So what we have been, what we try to do experimentally is try to essentially build models, which is the material model or the constitutive model, by doing very careful experiments and trying to selectively find those relationships between different objects. So let's go to the simplest case. Okay? Let's go to the simplest case of quasi-static deformation. But large deformation. So if you do a quasi-static large deformation, and you let's say I don't know. So let's say you take a dog bone sample, and you elongate it on one side. So this is maybe some sort of a rubber, let's say. So you can undergo super large deformations. And what you would do is you would look at this zone here. Let's say this zone has initial length of capital L, and you would measure the forces that are being applied on one end, and you would measure how the length changes of that small zone with respect to the force. Okay, so and then if you plot the graph. If you plot the force against, let's say, the change in length over the initial length, then it might, and you would do it quasi-statically, so you do it very, very slowly, right? So it would maybe, it might sort of show you behavior like that. That basically plot lots of points, and you end up having a behavior like that. So it's essentially, you can see it is soft in the beginning, then it becomes harder in the. You might do so. This is let's say for rubber 1. You might again do the same experiment for a different material, which might have a very different behavior. It might go something like this. And this is rubber type 2. So these kind of behaviors vary with the material that you have. But typically, this is how quasi-static experiments are done, that you do very, very slow stretch, hold it, do stretch, hold it for some time, do it slowly, and then you look at all these different points that you get from experiments. Then you might also say, okay, I want to characterize the material, so a simple elongation is not sufficient, because elongation tells me about changes in length. But remember, when we do our energy density function and elasticity, if you remember this, we did this a few days ago. We say that, okay, this is basically a function of C, right? And then we say this is actually a function of invariance of C, I1, I2 and I3. And if you remember, these three invariants have different properties. So I3 is linked to change in volume, and these two are linked to change in length and area. So a simple experiment which only measures changes in the length, which is the elongation experiment, will not be able to characterize everything directly. So then what people do is they end up doing other experiments. So they also do what we call as biaxial experiments. Which is basically having, let's say, something like a square. So there are many different ways of doing the biaxial experiments, and normally what they will do is they'll have a sample that essentially looks like this. It's very hard to draw, I think, but I'll still try. Yeah. So sample basically looks like this, and then you can apply traction or loading traction condition or displacement condition on these boundaries, and this would be a zone of interest, okay? Zone of measurement. And the reason I've showed that in the uniaxial experiment and in the biaxial stretch experiment, the zone of interest is somewhere in the middle, is because that's where you can sort of get nice deformation patterns. Everywhere else it will be extremely heterogeneous deformation. So you look at the zone of interest, and then this will tell you a little bit more about area, how the area changes. Right, so if you stretch it in one way or the other way, or in a combination of different types of biaxial stretches, you can get different types of force versus displacement curves in 2 dimensions. And then obviously you can also do a volumetric experiment. So that is relatively quite simple. Basically take a cylindrical sample, like a thick cylinder, and then you apply forces, and obviously it would deform to something different. It would also deform not necessarily as a cylinder, but it would deform maybe slightly bulging out, and then you measure the volume. So I think this So you can do all these three types of experiments. And then, then the idea is, if we are doing these experiments quasi-statically, we are only looking at the elastic properties of the system. And then you can try to identify what would be the appropriate energy density function. And let me write this down what I just said, appropriate energy density function. Now this has been a topic of debate for many decades. That for a given given soft material, and I have done some quasi-static tests, what is the appropriate energy density function? How do I find that out? So what people do is there is a whole host of different energy functions. Okay? So there is, and you can look this up. There is Neo-Hookean, there is Mooney-Rivlin, there is Ogden, there is Gent, Fung. Then there are some new ones by Holzapfel, Ogden. There are some different types from Aruda Boys. And these are just some of the functions that I can remember off the top of my head just now. For rubbers, all for exactly the same materials, all for exactly the same experiments. So for I think until the year 2015, so until maybe 10 years ago, and starting from 1920s, the main goal of this area of research was, so almost for like say 90 to 100 years, the main goal of this research area was, how do I come up with a new function so that I can fit all the experimental data nicely. So you have experimental data from this uniaxial test, from biaxial test, from volumetric test, and people have been just like proposing new and new energy density function every decade. There is a new energy function. And they have their own advantages and disadvantages. They have their own properties. So what was traditionally done was, you pick one. Let's say I pick one. I pick out an energy density function. It has certain form, and then I take all the data that is there, and I try to fit. I try to basically do the curve fitting. So there is something called as curve fitting. So basically, you've got a function, you've got some data, you try to fit your function to the data by solving a finite element problem. Essentially, you would require solving a finite element problem for this, and then you use basically a concept of least square error. And that would give you the parameters of the model. So it will give you the numerical values of the parameters. So typically plus error. So for example, Neo-Hookean model looks like this: C(I1 minus 3). So you've got to only find one single parameter that would characterize this entire material. Okay? Mooney-Rivlin has two parameters: C1 I1 minus 3 plus C2 I2 minus 3. So Mooney-Rivlin has two parameters. So you will do all the data, all the curve fitting to just find these two parameters. And then you will also spot some errors, and you will always, I think this has always happened, that no matter which function you choose, there'll always be some error associated with this curve fitting, and you will never like completely characterize everything inside this inside the experimental data, because that is obviously there is some error in the experimental data itself, because if you do the experiment, you've got some error bars coming in, and you've got some things there already. But at the same time, for a mathematical function to capture all this becomes quite difficult. So this is one way people have done it. Then there are some other challenges that come into picture. So this itself, for the simplest problem of elasticity, quasi-static deformation is the case. But then with soft materials, there are some extra challenges. So one challenge is the following: is that soft materials typically they are polymers. So if you look at rubber or elastomers or biological soft tissues like our skin or our muscles, they are polymers with long chains of carbon. Okay, so if I take a block and I zoom in to a particular area, I could probably see long molecule chains, long chain molecules. These are long molecules, all carbon-based or maybe sometimes silicon-based. And what happens is when you stretch and deform them, you get a lot of friction because of these molecules basically rubbing against each other. And that friction leads to phenomena which we call viscoelasticity. So if I do the same experiment, let's say, which I was talking about earlier, let's take the simple one. Take a dog bone sample and you are stressing it, but this time don't do it quasi-statically, but do it with respect to time. Okay, so this is the force, and this is, let's say, I'm looking at a length of this area. What you would expect is, let's say, this is how it happens. Let's say I increase the length I'll put time on the x-axis now, and I do the following experiment. Okay, this is my change in length over length, and what I do is I apply at some instant of time I increase the length quickly, then I hold the length same for some time, then I increase the length quickly, and then I hold the length for some time, and then I keep on applying loading like that. Okay? So this is what we call as a step loading. Where you increase the length, hold it, then increase the length again, then hold it, and now time is a factor. And what you would see is that the force that you need to hold to do this system. So first of all, as you increase the length, immediately the force would jump up. This is what the force is required. But then, if you keep on holding the length, the force gradually decays. And then you jump up again. And then it decays. And then you jump up again. And then it decays. So there is a very time-dependent response of the material because of this internal friction of the molecules. And this is called as, this is basically the hallmark of viscoelasticity. And we call this phenomenon stress relaxation. Right. So if you did a bit more dynamic experiment, let's say if you stressed and compressed and stressed and compressed, let's say. Okay, so if I plot my stress and strain for stretch and compression, basically this is what it would look like. It starts from 0, goes up, and then it just goes in a cycle like that. Oops. So this is what happens in viscoelasticity. And this area that is inside this graph is basically linked to the loss of energy per cycle. So viscoelasticity itself is another issue that crops up often. So in order to model viscoelasticity, there are many different approaches. Clearly, it depends on time. It depends on, and then we were discussing how do we bring in this approach. So what you can do is, if you know your maths from elasticity, your energy density function depends on F. You say that, okay, in the case of viscoelasticity, let me get an internal parameter which is called as Fv. So I'm not going to go into too much details of how do you do the modeling. I simply am going to show you a quick overview of viscoelasticity, and then you can see the relevant references. So remember, we had this reference configuration and a deformed configuration linked by an F. In viscoelasticity, what we say is, okay, let's take up an imaginary deformation. This is an imaginary configuration, Pi. And what basically Vi is it's linked to the reference configuration by a purely viscous dissipative dissipation, and from here to there it is a purely elastic motion, elastic deformation. So F is Fe Fv because of that relationship. And what happens is you can write down your total energy density into two parts. One is W elastic, which is what is preserved all the time, plus one is W, which is dissipative. So strain energy density is decomposed into a completely elastic part and a completely dissipative part. And then you apply the same logic. So what we were discussing earlier, you do experiments like this, these three experiments, but now you do them with quasi-static plus also rate dependence, because at the end of the day, your job is to find out what is this W. How do I find out the formula for this W so that I can actually get a material model for my material? So essentially, to get this model, you still have to do experiments, but now you have to have more parameters. So this will definitely have more parameters, because you've got parameters which are linked to this time dissipation, you've got parameters which are linked to energy dissipation, and so on. So the problem becomes a bit bigger. But this is very common in soft materials. And remember what I said here, that even for a purely elastic case, it has been very challenging for many, many decades. So for viscoelasticity, this problem becomes even more challenging. And then what happens is something more. And this is what is called as Mullin's effect. And what Mullin's effect is that when you're dealing with when you're dealing with rubber-like materials, okay? So this is very much commonly observed in rubber-like materials. What happens is there is a lot of damage due to large deformation. And I'll explain you why. See, a lot of industrial rubbers. Sorry, I'll just miss. Yeah, a lot of industrial rubbers. In addition to this long chain polymers, so industrial rubber, I mean the rubber that is in your car tires, or the rubber that is quite tough and it is used in many different applications. You have a lot of fillers inside the filler particles. So these filler particles are often sometimes carbon particles, sometimes harder metallic based particles. And as the deformation sort of happens, these particles go ahead and snap some of these chains. So what you would typically happen is if you just manufacture a new material in your factory and you start testing it. If you put, let's say, force versus some sort of deformation test on that newly manufactured material, you would have a trend like this. It will probably go up, come back down a different route. Okay, and then for the next cycle of tests, it will go up along the previous down route, go up, and come back down a different route. Then for the next set of tests, it will go down, go up in a different cycle, and come back here. So this is basically, it is called as softening. Your material has become softer and softer because of damage. So there are other more complex models to capture Mullin's effect, and basically what you do is when you manufacture a new material in the lab, in the factory, you do some cyclic loading on it just to remove all the Mullin's effect before it actually goes into actual production and actual product. So this Mullin's effect must be accounted for whenever you have a new thing that you make in the lab. And there are some other models for this that include damage, right? So my basic goal and behind just going through this different types of effects was, you can have Mullin's effect, you can have viscoelasticity, you can have pure elasticity as well. In all of these cases, the whole business of constitutive modeling, this becomes extremely challenging, and there are all these different ways of doing it by energy functions and by experimentation. Of course, you need a lot of experiments to do it. And in recent years, I would say maybe since last 10 years or so, we have had an exponential increase in computational power. We have an exponential increase in the capabilities of different data-driven frameworks. So one of them is obviously machine learning, but also many other different computational frameworks have become really powerful. And so this traditional techniques that I showed you, where people had some function that they liked, and then they wanted to fit to the experimental data, get the parameters of the function, that approach is now very old, and it is no longer state of the art. There are better approaches than that people have started using it in research, and I would just like to show you two of those in a very brief manner. Okay. So before I move on to show two of those, any questions? Okay, if not, let's continue. So one of them is machine learning based, and what it does is basically automatically discover.
So sorry to interrupt in between.
Yeah.
So one participant have one query, if you can.
Yeah. Sure. Yeah.
Sir, just like you said, in a new product that is made by the manufacturer, there is a
Yeah.
in new product there is a damage kind of thing, and there is a Mullins effect. So
Yeah.
so how they can before launching the product in the market, how they remove, means what are the precautions they taken and how they rectify these things?
Okay, so that's good point. So what I said was when Mullins effect is present in a specific type of elastomer, mostly rubber-like materials. Okay? And when you manufacture this, so the way you manufacture rubber, so there is a natural rubber obviously that you can collect from the trees, but then that's not the rubber that you see in the tires that you have. The rubber in the tires that you have is extremely, let's say, processed. So you would take that into the factory, liquefy it, mix it with a lot of fillers, and then basically mold that in the shape of a tire. So when you create that thing for the first time, uh, so when I mean create, I basically mean that these are when the solid, when the liquid polymer is mixed with all these fillers, and then when it is allowed to cure and it becomes a solid, this is what I mean by creation. And when it is created at that time, then it is in a state where it is prone to a lot of damage. So that product is usually, depending on what the material is, usually it is undergone a lot of cyclic loading. So what you saw in this graph, basically, if you can do enough cycles of loading, a few cycles of loading in the new product, then you basically come back to this state which is damaged. So this is a damaged state, and which would be basically the final state of the material, and then it is launched into the real assembly line. Okay.
Yes. Thanks.
Okay. But this is not true for all soft materials. This is basically true for a certain type of rubbers only. But because rubber is a very important industrial material, it is used all over the world in so many different things. This Mullins effect itself is a very important phenomena to work on.
That's fine, sir. We can go ahead.
Okay, so we were looking at constitutive modeling, and I was talking about two types of approaches which are now becoming very popular to identify how do I have the good model for my material. So one of them is this machine learning based automatically you discover the correct function. Okay, so I don't know how familiar people are with machine learning, but maybe I'll just quickly give you some basic understanding, and I'm sure a lot of you know a lot more than me, but I just to balance out the thing that I want to say, I'll just say a few things. So, and I'll just talk about, let's say, a neural network. Okay? So what a neural network is basically, or a deep neural network, basically a way to generate a complex function by function of function. So if you remember, let's say in mathematics you can have a function of x, then you can also have g, which is a function of x, which you can call as g of f of x. Then you can also have an h of g of f of x, which you call as h of g of f of x, right? And then if you want to calculate, let's say, dg dx, you would basically do partial derivative of g with respect to f and df dx. And basically this chain rule and all that. So this is basic mathematics, basic calculus that I think we have all studied in high school or maybe first year of your undergrad. So neural network basically have very similar concept. So what it does is you have something as an input. So it can be a single x, or it can be x1, x2, x3, x4. So it can be a scalar input or it can be a vector input, doesn't matter. And similarly, the output can be a single scalar or it can be a vector. And the idea is, how do I write this vector y as a function of vector x? I want to basically find out the functional relationship between the output and the input. And the neural network does exactly that by introducing a lot of different layers in the middle. So you can have, 1, 2, 3, 4, whatever many layers with very different number of, and it essentially connects. So here to here, if you go from x1 to, let's say, I don't know, let's pick a number, let's say a1. Okay, so this is layer A and this is a1. So x1 to a1 would be a function, a1 of x1, and then from a1 to, let's say, b1, this is b2, and so on, this is a2, this is c1, c2, and so on. So b1 to a1 to b1 would be another function, and then this would be another function, and then this and this would be another function. And basically you would look at all such combinations. So you can go from x1, a2, b1, c1, y1, or you can go from here to there, or you can go from here to there or there. And basically, if it's a fully connected neural network, all of them will be connected to each other, right? And then you've got all these functions, and all these purple lines that I have drawn. These are just some functions that are there. So usually they can be linear function, they can be a hyperbolic tangent function, they can be quadratic, anything that you can think of, right? So there's all these functions, and a neural network tries to find out this relationship by combining all these functions together, right? And this is the central idea behind machine learning, is that I want to find out the exact linear combination of these functions so that I can approximate my model. So in a machine learning problem, you would put this thing into an optimization system, and it will tell you the exact weights. This is what they call as the weights, or the exact numbers that are associated with these circles to approximate. Finally, the output is, you want to find out what is the correct function that relates input to the output. That's the central idea of a neural network. So in this case, what we do is, and now I want to share my other screen to give you some idea about this method. Maybe before that I share something else. So in this case, what we want to do is, we want to construct, our goal is to construct what is the correct energy density function given some deformation gradient. Okay, this is what we want to find out. And of course, you can apply the same logic to viscoelasticity and other complex problems, but let me start with the basic one. My goal is to find out what is the energy density function as a function of deformation gradient. And I also know that this is basically not a function of f, but a function of I1, I2, and I3. So what people would do is basically create a neural network like this, and fill this up with different types of functions. Okay. and then try to match this to the experimental data. And then, once you have matched it to experimental data, you've got some W of F that sort of resembles the material model. Then you would link that to all these family of energy functions that you have here. And then you would extract from this what is the most probable energy density function for the problem. So remember what we were doing earlier. Because we were doing things manually, people would just pick up their favorite density function, try to the data, try to match your favorite energy density function to the data, and then get the parameters for your favorite energy density function. But now what we are doing is, we are trying to get the probability of multiple energy density functions that have the best fit to the data, and then for each of them we are getting the correct set of parameters by doing this machine learning algorithm correctly. So I'll quickly show you the relevant paper that has done this, and you can look at that paper and learn. So this is this paper by this group, which is out of Netherlands and Switzerland, and this Euclid is a framework basically, and it stands for efficient, unsupervised, constitutive law identification and discovery. And the good thing is, if you look at this paper, they are recording the lecture, so obviously everything is there with the recording. You can go to this link here, and there you can download all the codes which are in Python, and you can run those codes, and then you can do some experimentation yourself. But the idea is the following. So you take any unknown material and you do some experimentation on it. Okay. So you apply some forces and displacement, and basically what you can measure is only either the displacement at the boundary, or you can measure the forces that you apply at the boundary, and you can also measure two-dimensional displacement of the points on the surface of the material with the help of digital image correlation. So with that displacement data, you try to create a mesh, create some individual displacements, and from those displacement you get displacement field. From the displacement field you get a strain field, and then on that strain field you choose one of the neural networks, which is basically an energy density function. So a neural network now has the role of energy density function, right? So you take the strain, take the energy density function, which is a neural network, and that gives you the stress. And you can do that not with just one energy density function, you can do that with an ensemble. So you can take all the different possibilities that you want to consider, take all of them together, get all the stress fields from each one of them, and from those stress fields you get the boundary condition, and then you match this boundary condition to what you applied in the beginning. And you want to basically do an optimization so that the boundary conditions that you have as an output of the neural network matches what's there that you applied in the beginning. So you run through this loop a few times in an optimization framework, and that tells you finally what would be my actual energy density function that will be output of this process. And for that energy density function, you get the correct set of parameters. So I've just said these things in a very simplistic, general manner. Obviously, there is a bit more complication going on behind the scenes. But if you are interested, you are welcome to read this and papers similar to this topic. So this is not the only one, but I've just picked this one because it's a nice one. The codes are available online, so you can play with the codes yourself. And here is the basically what the neural network looks like. So this neural network is slightly changed than what we are used to in machine learning, and mainly because of the constraints of elasticity. That elasticity requires that all the functions are polyconvex. So polyconvexity and some other things basically mean that not only all these layers are connected with each other, you also get a connection going from the first layer to the second, from the first layer directly to the third, and to each one of them directly. Okay, so each one of these layers get a contribution from the first layer directly. So this is what is called as a ICNN, which is input convex neural network. So I can show you maybe a couple of they have some results. So they have done an experiment where they take a plate with a hole, do some displacement, and then essentially they predict energy density. So these are three different energy density functions: Neo-Hookean, I think Ishihara, and Holzapfel something. And basically you get different probabilities, and then you can also take in fiber reinforced materials, so you get different fiber directions. So this is the original paper that was there. I can also show you another paper where this method was used. Just give me 1 second. Yeah. So the same method was applied for discovering the correct material model for a brain tissue. A brain tissue is a very complex soft material, very hard. In fact, any biological soft tissue is extremely complex for a whole host of reasons. I mean, they're heterogeneous. They're always embedded in some sort of a fluid, and things become complex. So they applied the same technique to find out the interpretable model for brain tissue, and then let me show you what they have done. Basically, all the mathematics is there. For if they have, yeah. So here are some of the experiments that they did. So they actually did experiments on human brain. They take out some small specimens. They run it through. So this is what is called as a rheometer. So rheometer basically it takes a cylindrical specimen or a disc type of specimen, and it does shear loading on it. And the time-dependent shear loading basically captures not just elasticity but also viscoelasticity. So they are doing actually time-dependent viscoelastic characterization, and this is what you can say the real experimental data looks like. It is very noisy, obviously quite complex to model, and in olden to do characterization of this kind of material by choosing some energy function that was our favorite. But now you can actually systematically obtain the most probable energy density function. So you apply this carefully, and then let me show you the results somewhere. So basically, okay, this is very hard to see, but these are the results for different types of material parameters, or different material parameters. I don't expect you to read it just now. I'm just showing it here so that it's there on the recording, and then you can go back, and if you're interested, you can go and read this later on. But this is just to give you an idea of the things that are possible with methods like this. Okay, so that was the first method that I showed you, which was, let's say, uses a little bit more modern technology to in a systematic manner you kind of identify the correct set of energy density function that you need. Okay. There is another class of another philosophy in this area, uh, and there is a whole host of scientific community that is on a different side. And what they say is, and you can make up your own mind. I'm just giving you different perspectives. Okay? So what the other side of community says is that it is not a good idea to try to find a nice mathematical function which is material model. So what they say is, at the end of the day, you have to do a finite element modeling. So how about we directly work with the data? Let's ignore this intermediate step of developing a costive model and getting an energy function. And this community, they call it a data-driven or a model-free approach. So let me quickly get that paper out, and I can show you what their so this is a very famous scientist in computational mechanics. Some of you might know this name of Michael Ortiz. He's based in Caltech, and I mean, this paper first came out in 2015-16, and since then, I mean, this idea had been around for a while, but this paper came out in 2016, and it gave like a nice set of methods to work in that direction. And then people have been following this and extending this for all sorts of problems, and not just elasticity, but viscoelasticity, plasticity, complex problems. So the idea, I'll just quickly show you the overview of the idea, and then again, if you're interested, you can go deep into this. So overview of the idea is the following. I mean, and they have shown this through simple experiment with a truss bar. Okay? So if you plot stress and strain for a single bar, you will get some data points like that. And obviously, the traditional way is we try to fit a curve through this, and then that curve becomes our reality, and then we use that model everywhere. And what they say is, why not directly use these data points in our simulations? So the data-driven solver has the following, that you define some, okay, let me put this way. So you define a problem like this, that you want to minimize a certain energy, but now instead of having like minimization is what we talked about earlier as well. You eventually pose everything in terms of a minimization problem, but now instead of having a model, we want to minimize our energy such that all the forces that we predict, or all the stresses and strain that we predict, are as close as to this data rather than to the model. Okay, so that's central idea. So, and then I'm again not going to into too much detail of this. There is some algorithm that you can see. And they've shown this via. Okay, so in this paper they have taken a truss, but you can also see elasticity. What I want to show is there a code here as well. I think if you go into this paper, they also have supplied. I can try to find this where that is. Maybe I can find and share that later on. but I'll come back to the original part of this paper. Yeah, so if you look up this paper, you'll also find the associated set of codes to kind of help you go ahead and work on this problem. Right. So I think this is where I would like to maybe pause for a bit, and just to kind of say that the idea behind this part was to show you that modeling, like getting the material model, getting the actual behavior of how do different fields, stresses and strain or strain rate and friction and other things behave in a soft material, getting a correct model is extremely difficult, and it has been a challenging problem for decades. And I just showed you a couple of examples of elasticity and viscoelasticity. We have also been talking about electromechanics and magnetomechanics, and the models for electromechanical coupling and magnetomechanical coupling are extremely poor that we have right now. They just don't work properly. So with the experimental data, we just have something that we have, and I think these new approaches that I just showed you, these two ways of going about, I think these are quite good. And these, if you are, and because you are, all of you are, like, let's say, starting your research career, if you choose to work in this domain at some point, then my suggestion would be to use these advanced tools, these tools which are for the next generation, and if solve these problems efficiently. So tools like open source software, DL2 or Euclid or this data driven, or maybe you will find something else. But try to look at what's coming up now rather than what has been for many decades. And that's the only message I wanted to deliver. So that's where I'll stop, and I'll see if you have any questions.
So any query? So sir, nowadays I have already seen that there are different network models. So we are having physics integrated neural network, artificial neural network. In today's session, I have explained that we are also utilizing this ANN for predicting, like we are having some data sets, and for prediction of the other data set instead of carrying out the experiment again and again and finite element solution. We can use ANN and physics integrated. So sir, how judiciously we have to choose which neural network like fit to our problem? Is there an initial way we can guess that if we are go with the physics integrated or artificial neural network, that it is well suited for our soft active material problem? So how we can select that network model?
I think one should be really careful when dealing with this new thing. So there are some physics integrated neural networks which people have developed just because they wanted to work with neural networks. Okay, so I think a lot of people do machine learning because it's a fashionable thing, and it is, they just want to work on it rather than having an actual use of things. So the things that you have talked about, I don't know exactly what they are, but my suggestion would be try to use the correct tool for the problem that you have always. So rather than a general tendency among people would be, I have this tool, I really love this tool, and I want to use this tool for everything. So that can be, I have this mathematical framework, I'll use it everywhere, I'll have this neural network, and now I'll do everything with machine learning. I think we need to be aware of trying to be a little bit more judicious and trying to say, I want to use the correct tool for the correct problem. So let me analyze the problem. If your problem has a lot of data, and if that data is hard to interpret, then neural network is a very useful tool for that problem. But if your old problem has already a very good solution, so for example, if you're trying to solve a partial differential equation, finite element method is a very, very efficient and powerful solution for that. So for that, you just use FEM. You don't need to go to a neural network which is trained on an FEM anyway and go in cycles. So this would be my suggestion, that whenever you pick up a problem, just try to do a little bit of literature survey and try to find what is the correct, what would be a nice tool to have to solve this problem with. And then I think you can answer your questions that way.
We are anticipating this answer from you, sir. Thank you very much. So, online participant, if you have any question and query, please free to ask. It's a last chance. Sir is here with us. It's not a last chance. You can mail to him. You can interact with him. But right now he is joined online. So, if you have any query, you can ask. So, sir, we have one question here.
Yeah.
Sir, you said that these data-driven method, like the experimental data, we can model by our own depending on the experimental data. We not need to go with the new Hawkian or whatever existing models are there. So
Yes.
every time a researcher is doing something, he will be performing the experimental data and he will be extracting the results and doing the data-driven approaches from his experimental data. That's so it will be a loop like L10. These kind of things are already stabilized things. So this must be like there will be standard must be there now. There like every researcher is doing their own experiments and doing their own data-driven approaches. How there will be a standardized approach that they are doing the correct thing? How there must be correlation between these researches now? That's what I'm asking.
That's a very good question. So let me kind of reinterpret that a little bit. I think what it boils down to is how do we create a centralized universal repository for experimental data for different types of materials. So just like what we have done for these mathematical models, we have mathematical models like Neo-Hawkian, Mooney-Lewin or Ogden. Now I think what we, as a scientific community, what we can do is, given a certain material with a certain chemical composition, can different groups in the world, can they do their set of experiments and publish the experimental data in a data repository? And I think if that can be done in a systematic manner, then you can use those data-driven approaches to extract the data and basically solve the problem that you have. If everyone does their own experiments in their own lab, I think it's a good thing, but also it should be done with some sort of standardization in mind, because my personal experience with experiments is that if I pick up a material and I take it to lab A and do something, and if I take it to lab B and do something, I'm likely to get different results because the calibration of equipment will be different. The temperatures might be different, and so there is a lot of variability often in various things. So I think the quality of data is a very, very important issue here. If you can kind of, in some way, by some standardization, if we can guarantee quality of data, then I think these data-driven methods would perform really nicely. But their behavior completely depends on quality of data.
Obviously, sir, that's what I'm saying, that if we keep on increasing the data depending on the random experiments that people have carried out, it won't be a good practice if we are applying those data-driven methods.
That is true. So think of it like this. So when we publish a new mathematical thing, it undergoes peer review, and only then it is published. I think we can do something similar to experimental data, that if you publish experimental data, it undergoes peer review in different labs, and then once it is confirmed that yes, that is indeed a correct set of observations, then it is published into a central repository where people actually use data from. So like you have a journal of papers where, so you can download, I mean anybody can upload any paper on archive, but you go to a journal's webpage and download a paper from journal because you know that it has been peer reviewed and it has a certain quality of it, right? So same thing can be done for experimental data, that anybody can upload experimental data from their lab, but if it undergoes a peer review and it has been, then it can be published in a certain area which is managed by a group of scientists, and then we can use that quality assured experimental data, if that makes sense. So that requires sort of so this thing, by the way, is already done in many other fields. So in computer vision, in other domains which are let's say 15 to 20 years ahead in machine learning, this process is already followed. But I think in mechanics we are very late to the party, so we are still trying to figure out what do we do with machine learning and data and how do we do it efficiently. So I think we will come there, but it will take some time.
So any other question? So sir, participant here, online and in person, just want to wish you a very happy Teachers' Day. And
Yes, thank you very much for that. Yes.
And thank you, sir, for it's a really being an interactive session throughout the course. We really like the spirit, and we are really looking forward in the future for organizing such course. So we will have your presence. In the future, we want to be in person here. That will be of great pleasure for us, sir.
Absolutely. I mean, I'm a bit sad that I could not come there in person because of these conflicts, but definitely I would love to visit you and hopefully we can have more engaging discussions like this. And hopefully I did not bore you too much with all the things that I said. And good luck for your research careers. I'm sure I can see a lot of bright faces there, so I'm looking forward to read nice things that you guys write later on in life.
Thank you very much, sir. Thank you very much for your motivational words. So, if anything, if you have any queries, still you can ask, or otherwise we will have your exam. So, sir, we are planning to conduct a short exam that will be like basically based on the question that they have learned during the entire course. So that we are planning to conduct now. If you have any question, online participant, you can ask.
Hello, sir. I want to ask a simple question. I have been working in quantum mechanics in same field for constitutive modeling, and I have done it only analytically. And now I want to learn APM in a way that I can learn giving less time and get much and verify my existing model which I have developed. So what will be an ideal way to learn finite element analysis with hands-on experience with the software? As you said that today you showed us a link that we can use some prerequisite codes are there. So what will be a good way so that we can grasp the thing technically as well as computationally?
See, so if you want to learn finite element method, that is so there is no alternative than to basically take a nice textbook or take a course in that. Okay. So just to understand the fundamentals, because understanding that is super important. Then the next thing is using finite element method. So for using finite element method, there are obviously many options. There are very easy to run these Abacus and commercial software. But then as you said, there are different. You need to balance out what is it that you want with the software. So what I showed in the beginning, DL2, it's a very powerful piece of software, and it is freely available. So, but it also requires a little bit of knowledge of C++, and it also requires a little bit of commitment from your side, because whenever you do computer programming, and because you work in mechanics, you are familiar with the mathematics at least. The same thing happens in mathematics, that whenever you take up a new thing, you end up making a lot of errors. There's a lot of trial and errors, and it takes time before you become efficient enough to run it and do your thing. So same thing with DL2 or C++, that if you're new to C++ and if you're new to DL2, then there is a learning curve. There's a steep learning curve, but once you're past that, I think you can do things quite easily. So it also, another consideration you should take into mind is what are your long-term goals. So if in the long term you see yourself using them, then I would recommend going ahead with tier 2. If your goal is just to use FEM to verify some small thing and then move away, then I would not invest a lot of time learning DL2, but I would basically do something simple in Abacus. That would be my strategy. But I would say learning, if your goal is to learn FEM, then there is no alternative but to pick up a textbook and take a course in that.
Thank you very much for the answer, sir.
So, participant, do you have any further question? No question? Sir, we don't have any further question. So, I hope, thank you very much for your such an interactive session. And if you say, sir, then we can start conducting a small test for the candidate here.
Yes, absolutely. So thank you so much. I will log off in that case, and enjoy the rest of your time. Have a good weekend. Have a good exam. I'll see you later on.
Okay,
Bye-bye.
thank you very much. Thank you, sir. So online participant, soon we are going to share via email. You can check a small quiz or an exam to you. That will have 10 objective questions. So you have to answer that and reply back on the same email ID from where you will get the question paper. So don't reply all, just reply to a single email ID. You have the 15 minutes, so it's 3:45. Up to 4 you have to submit it back. And it's very, very important to get you, so that we can give you a grade sheet along with a participation certificate. So along with that, we are having a feedback form also. So in that feedback form, you have to also reply back to the mail from where you will get that. So that you can take some time after giving the test, you can supply back the feedback form also. So thank you very much. Now we are going to share the test with you. You can check your email IDs. You will receive email. Because it's all sent to all the participants. Spam also.
Audible to you.
Yes, you are audible.
Sir, how to this?
It's like very simple. We have sent a PDF one. You just tick the answer whatever you save it, reply to all. And immediately if you complete it, you just feedback form also and send back. With the test, you can send the feedback form also on the same email ID. Yeah. Thank you very much. So I request to attach the feedback form along with your test paper response. Otherwise, you keep on sending two different mails. So it will be easy for us to track. Just in a single email reply, send your test response and the feedback form. Thank you very much. Great. ये नहीं कि copy करना. Whatever you have learned, just answer that. Please don't.